Yeah, I would say so.
Okay,
yes.
okay, you see. Okay.
Okay,
Okay.
so yeah, our second speaker is Alexey Koshelev from Korea, Interior, and we speak about ghosts in ghost-free analytic infinite derivative gravity theories. Please, Alexey.
Okay, thank you very much. Thanks for organizing all of this. It's a lot of mess. Thanks for opportunity to give a talk. And yes, I will try to speak about ghosts in what is claimed to be ghost-free infinite derivative gravity or non-local gravity in some sense. And this is a little bit controversial and provocative title. So let me say that this is based mainly on recent activity by myself in collaboration with Ravan Kumar, Alexey Starobinsky, and Anna Tokareva. And what I will be talking about is, let's say, more questions than some definite answer, as often happens. So let me just introduce the problem, why at all I'm in this business and why at all of us are now gathered for this nice workshop, because we know for a long time that Einstein gravity, whatever we like about it, it's still not UV complete. And during this workshop, we mentioned a lot of time a great development by Kelly in 77 and 78, and very brilliant papers which show that R-squared gravity is renormalizable. But unfortunately, this also features not very nice presence of a ghost, which appears in spin 2 sector. So we must somehow understand this theory better and find, so the idea which drove me on this road is to see whether we can improve this nice proposal. And moreover, we know that R-squared models in general play a lot of role, and Starobinsky inflation is one of the brilliant model out nowadays, which shows how R-squared inflation drives universe and that it works. And on top of this, there were interesting developments by many people, starting from Krasnikov, whose talk we were happy to hear just now, Kuzmin, Yefimov, and then by Tumbulis, and nowadays by also many people, including Arefyeva, who had pleasure to have yesterday with a talk, and nice papers by Barvinsky, Biswas, and many others who are in this list and not only in this list. And the point is that sometimes we see how non-locality or in principle high derivative operators help to improve situation, especially with UV regime. So the idea is, can we somehow join R-squared gravity with high derivative operators such that the main problem, the problem of a ghost, is cubed? So definitely I'm not going to spend a lot of time on details, and because many of you are working on very related subjects. But what I want to stress a development which once was done by myself in collaboration with Tirto Biswas and Anupa Mazumdar, which was quite simple conceptually, but which led us to a very nice observation. You see here in the previous slide, I mentioned words about string field theory, which is indeed a nice theory, which contains non-local form factors. But let's think, let's say, simpler. You see, let's take some action. This is a very much generic action, which contains these letters P, Q, and O. P and Q, something which built out of Riemann tensor, and O, something which is built out of covariant derivatives. Question which we have put is a very simple. Imagine everything depends analytically in infrared regime. So it means that we have well-defined infrared limit of this particular gravity action, which, as you can imagine, includes everything. The question is, what would be the essential part of this action? What would be the most important piece which describes your dynamics around maximally symmetric spacetime? Why maximally symmetric spacetime? It's kind of obvious, because we live in nearly Minkowski space. Even if universe accelerates and we live in de Sitter, inflation happened, and the main part of inflation, the most important, was the de Sitter expansion. So we very much interested in describing this particular set of spacetypes. Even though we know now from Guy et al. That maybe de Sitter is not that much physical space-time or background, still we have to somehow survive with the understanding that observationally we are somehow there. And this is a result of computation which was done in these two papers cited here. And the result, which is purely algebraic computation, quite long, but without any conceptual difficulty, is that this is the essential part of what you have to consider. This is what is the main part of any gravity theory, which is, and these particular two lines are responsible for linear perturbations. Linear perturbations, in turn, is everything what you need to know to consider things like, for example, Newtonian potential, perturbations during inflation, stability, spectrum, stuff like this. Okay, so the goal was quite nice, and we achieved it by saying that this is what we have: Einstein term, lambda term, maybe, and then these three terms, which are practically R-squared pieces sandwiched with some functions of the Lambertian. These functions of the Lambertian, as written here, they are analytic at 0 in the argument, so it means that infrared limit is obeyed. L menu is just a technical redefinition of Ricci tensor. It's just a little bit more convenient. And the next step, which was done not in this paper, but in some other paper with Sravan and with Alexey Strabinsky, is the fact that in principle, around maximally symmetric spacetime, one of these three terms can be cancelled due to Bianchi identities in D equal 4. In D greater than 4, it can be made local. And in principle, this one in the middle, containing second rank tensor, is the most difficult in computation. So if we're going to cancel something, we're going to cancel this. So in the sequel, I will not consider this term at all, because I'm interested about dynamics around some maximally symmetric spacetime. And so first piece, R squared, and last piece, Weil squared, is present. Yeah, W, I didn't say this explicitly, it's a Weil tensor. Weil tensor is also a matter of choice, but it is convenient, because when you have Weil tensor, then your theory is, as long as you consider conformally flat metric, then Weil tensor is 0, so it is convenient. And quite a natural step, which was done, of course, it was to write the propagator. And here how it looks like. And spin 2 is a very important piece, because this is where Koshelev observed a ghost. So this is what we have derived from our action. And the bottom line, what Koshelev has in his proposal, where Weil squared tensor, local Weil squared tensor, is inserted in the action. The point is the following: Weil squared local was necessary for Koshelev, because otherwise, because this was a this is how renormalizability is gained. It's a counter term. But you see here in our setup, situation is way different, because yes, we have this piece, the green one, which is just from local part of R squared. So technically just F0 coefficient from this expansion of function Fr here. And also we have this piece, is the whole third term, where the red multiplier is exactly this function Fw. And R bar is some background curvature, because we are speaking about maximally symmetric spacetime. So let's say it may be de Sitter or anti-de Sitter. And this is a whole difference with what was obtained by Stella, because for Stella, Fw was just equal 1. So in case of Stella, this operator P of box reduced to this line, which is just first degree polynomial in box. And as such, you clearly see appearance of two poles here, as long as you have one here. So FW equal unit is not something what you like. Why? Because we pretty much know that every next multiplier with box here will introduce a new degree of freedom. And if the first one was okay, the next one will be a ghost. And this is Ostrogradsky statement known for a while. As such, first of all, we see, yes, indeed, that we have changed the things, but it's not obvious at the moment whether we have succeeded, because it's not obvious whether we can do anything with all of that. But yes, the answer is that yes, we can. And I will now go to answer how it happens. And well, before technical answer, I just mentioned that the same goes about spin zero, things are fine, and we derive formulae and they coincide with local counterpart as long as FR equals 0 or constant. So everything looks nice, and FR equal 1 restores us scalaron, the scalar degree of freedom. And so here things are more or less understandable and don't worth too much attention in principle. What does worse, however, is that you see, we are introducing here high derivatives. This function introduces explicitly higher derivatives. We don't know how many we need, but we know that something more than two derivatives is not obligatory, but at least initially considered bad, starting with Ostrogradsky analysis of 1850. And then, however, we go forward and we understand that it's not hopeless. Hardesky model is a model which has high derivatives in the action, but it's not so bad. The equations are of second order. String field theory is a consistent example with high derivatives and form factors, but still in all these setups, you see, we kind of have local propagators and we have second order equations. Here, it's kind of obvious that we will have higher order propagator and we will have higher order equations. So the question is there a resolution? And the resolution is following, let's say, pioneering papers on non-local field theories, which I mentioned in the beginning, and about which we have also learned from the previous talk. The resolution is that in principle, yeah, you can promote your box minus m squared kinetic term of some scalar field, and I consider here scalar field as a model, to some g of box. And if you do it, let's say like this, like two multipliers, box minus m squared, box minus mu squared, nothing funny is happening because you just introduce new degrees of freedom, and second degree of freedom is a ghost. Things change if you introduce something like exponent of entire functions, then you are indeed much better to go, because entire function is a function without zeros. As such, entire function is a function without singularities on the complex plane, and as such, exponent of it doesn't have zeros. So exponent of entire function is somehow special entire function, which doesn't have zeros, no zeros, no singularity on the complex plane. So no finite poles for the generalization. It means no new degrees of freedom, but of course something should be sacrificed, and we will see what happens. But just before we will see explicitly, I will mention that indeed, string field theory is something which provides us with a kind of similar picture. This is schematic Lagrangian, which you could get from a string field theory, which usually has all these non-local operators in the vertices, but at least at low levels for some restricted string field theory description, when you cut all massive fields out, you can say that, okay, upon field redefinition, things are more or less identical to getting non-local propagator. So maybe we indeed can bridge what we observe here with something more fundamental like strings. But you see what I meant to say before, even without strings from gravity, perspective of view, we see that high derivatives is kind of generic thing which would be considered. And we see that in order to tackle ghost problem in stellar setup, it may be good. We will see now whether it's good or not. But before we see this, let me remind you some trivial facts about entire function. So since I believe all of you know what is entire function, I will not spend too much time. The main purpose of this transparency, of this slide, is just to emphasize a very important point. Exponent of entire function here, you see, exponent of entire function. It's an object which necessarily leads to essential singularity. So yes, we have avoided poles in the finite complex plane. So for finite values of the Lambertian eigenvalues, there will be no pole, but we gained maybe a problem, which is essential singularity at infinity. And this is exactly where all these canonical things like weak rotation or whatever break down, and we have to invent somewhat new. What we can invent and what, for example, about scalar field models was already outlined pretty nice by Ashok yesterday, and some explicit example will be soon, if I remember, on Friday, considered by Anna Tokareva, my collaborator, where we considered how it works explicitly and how we can maintain unitarity and stuff like this. But returning to gravity stuff, and understanding now that we play with some exponents of entire functions, let's see what happens explicitly for spin 2 field. And let's go for a bit simpler setup. Don't bother about generic maximally symmetric space-time. Let's say Minkowski, and as such R bar equals 0, background curvature, okay? So this is what graviton propagator looks like. And this is what operator P of box reduces to. The form is pretty simple. So we just have learned that in order to maintain the physics, to preserve 1 degree of freedom, to avoid extra degrees, which would be ghosts, we must just identify P of box with some exponent of entire function. So we just have to resolve this algebraic equation backward with respect to Fw. Everyone can do it. The only one restriction arises that omega at 0 must be 0. This is to guarantee infrared limit, because then Fw is analytic at 0. Okay, so you see, we have gained something. So we somehow improved the proposal by Stella. We inserted here a form factor, and you see this Fw, which should be in the action, is obligatory infinite derivative form factor, and I cannot say that I see any way around of this. So I agree absolutely with Ilya Shapiro that high derivatives must present, but in my opinion, it's infinite derivatives must present in the action, because algebraically everything is transparent and clear. And yes, we have gained ghost-free condition around Minkowski background. So theory is great, but can we speak that we are on the way to quantum gravity? Can we say that we are ready to quantize this particular action? And here I want to go a little bit to the part of concern, which is as follows. You see Minkowski, so you see, when I say that I want to quantize this particular action, I just want to say that, yeah, I want to enjoy I want to entertain myself somehow with the fact that this particular action formulated here is something great and good for quantum gravity. And maybe it is. And maybe we can prove it with time, but you see the point. I would be happy then to see that it's not only Minkowski, but rather any classical background in this theory is well defined. if I want to do it, then first of all, the question is, do I have other backgrounds? Because it's not obvious that you can solve equations of motion easily, but in fact you can. And this is an example how you can obtain solutions. And if you substitute such a condition, box R equal R1R plus R2, your equations of motion, then upon these algebraic conditions, which you have to impose on function fr, you will get many other solutions. If you know, if you can recognize here quickly, this condition is nothing but R squared equation of motion. I mean, equation of motion of local R squared gravity. So the claim is very simple. As long as we consider solutions of R squared gravity, all of them can be embedded as some solutions here. Okay. Well, for the moment, I'm speaking about conformally flat backgrounds for simplicity, but definitely it's already a lot. So we already have a lot of different backgrounds. Moreover, in our paper with Sravan and Starobinsky cited here, it was mentioned, it was put as a proposal that in principle, from pure mathematical point of view, we can show that as long as you demand that the Lambertian operator on your manifold forms a complete set of functions out of eigenmodes, then in principle, this actually the set of all possible solutions. But this point is, let's say, a little bit questionable because you are not always living in a space which has the Lambertian operator forming full complete set of functions. And in fact, even for the theta, it's not very easy to show because it doesn't have the Cauchy surface. But whatever it is, we already know that we have a lot of solutions, and we even have idea how to think about the whole space of solutions. But the point is that we have many solutions. And here on the previous slide, it was clearly shown that we can do things great for Minkowski case. Okay, so it means that technically speaking, making things great means at this stage having no ghosts, and having no ghosts technically implies fixing your form factor fw, and in other case, fixing this function fr for scalar modes. But fw, at least, consider at least one function, consider simple thing. Yeah? So you see, we fixed it demanding something is good around one background without actually accounting what happens around other backgrounds. And the question is, can they be ghost-free? And so what is the summary for the moment? For the moment, we can say the following, that yes, we have some very generic model which describes maximally symmetric space-time, whatever gravity theory you started with. We have shown that pure algebraic arguments tell you that you must have infinite number of derivatives to defeat the spin to ghost. Then you can make it ghost-free, the whole setup, around Minkowski only. And then it's nearly obvious that if you fix f of box around some background, that ghosts will still present around other backgrounds, because algebraically you need for every next background compute your u and u condition for f of box. So what can be a resolution here? The first resolution, which I don't like too much, is that maybe the word quantum and construction of quantum theory is a little bit too early to say here, but there is another point that in principle, even if we can have somewhat new degrees of freedom around other backgrounds, first of all, we can make Minkowski great. And second, even if we get ghosts around other backgrounds, let's see what the structure of them. and what happens to them. So let's see what kind of problem we gain with this construction. And
Alexey, sorry, you have 5 minutes.
Yes, thank you. And so the idea how to treat the problem appeared in a kind of other study where me and Anna, we were studying non-local Higgs inflation improved by insertion of non-local operator. It was done in this paper cited at the top. And what I want to say, it's not about Higgs inflation, it's about the method which we used and what we gained. And the idea is the following, that this is the Lagrangian which we had to consider. Whatever it describes, at this point, it can be said as it is a Lagrangian of a scalar field, minimally coupled to gravity, to Einstein gravity. And we have inserted some form factor to improve UV behavior of scalar field. Great. This is how we learned some slides before. Sigma must be an entire function. So what we know pretty much that we can, in principle, make the system ghost-free in some background, in some vacuum for field phi. And in this particular case, we made it for 0 and infinity, how it should be for inflationary potential. But it cannot be done for every point of the potential. So if we consider evolution of our field between vacua, and then we, some interpolation between two, let's say, good vacua, we necessarily pass stages where we have a new degrees of freedom. Appearance of the degree of freedom is clear. It's this equation, because this equation tells us the masses of degrees of these new degrees of freedom, and actually how many roots you find, so many degrees of freedom you have. Roots, I mean roots with respect to box. And as long as it's considered, if there is 0 on the right-hand side, at any point when there is 0 on the right-hand side, there is only one root, box equals 0, which is massless in this case, field. For all other points, as long as the second derivative of a field is not 0, you will have infinitely many degrees of freedom. What are these degrees of freedom? Well, half of them are ghosts. Yes, they are ghosts. But what we could demonstrate clearly that thanks to this coupling to gravity with scale of Planck mass, it surprisingly follows that these ghosts, first of all, become extremely heavy, at least heavier than Planck mass. And second, what you can deduce that if you approximate some stage of evolution of your system as a de Sitter stage, or anti-de Sitter, it doesn't matter for the moment actually, with some scale factor h, then in principle, this is the relation which should be obeyed by mass of a new degree of freedom, such that this new degree of freedom is classically stable. Classically stable means that classical solution is not growing. So here, technically, it means that imaginary part of mass squared and all of the squared should be less than 9h squared multiplied by real part of mass squared. And all these masses appear, all these mass squared appear to be complex. So they're not real. I mean, mass squared is not real. Sync is not very well understood. It clearly leads to what is widely discussed here, which is non-diagonalizable Hamiltonian. But what is important to understand at this point is the following, that first of all, we have clear condition how to make these modes classically harmless because they are not classically growing. Second, they're extremely heavy. So most likely, in combination with the fact they are classically stable, not growing, I mean, it's very easy to make them such that they don't influence our system. They already put far away from what we observe. And the third point, which I want to mention, is that we have to understand that this condition arises absolutely, it does not depend on the entire function itself. This condition just arises as a solution of second order wave equation in a given background. What is indeed related to shape of entire function is how many roots we have here and precise values of these masses. So precise values of these masses appear from mostly from the shape of this entire function, but the condition that they are better to be like this is not related to entire function, and this is only our wish to have these modes classically stable. So it's independent condition, which in principle, we are happy to arrange as long as we can adjust our entire function. So you see what I want to say as a concluding slide. Yes, we have discussed for a long time in general, and in this talk, I try to present some class of analytic infinite derivative theories. And the main target of this infinite derivatives is, of course, ameliorating UV behavior, improve it, get rid of singularity, divergence, etc., etc. In fact, there are nice properties for these models, and classically we have many interesting things like embedding of Stravinsky inflation, Newtonian potential, some other papers in which I collaborated as well, discussed non-singular bounds, etc., etc. But for the moment, there is something salty in this approach, because you see, it's not very well understood, at least from my perspective, how it can be defined for all possible backgrounds, or whether how we should meet appearance of heavy but maybe benign ghosts. And we have an idea how to make them benign by arranging special entire functions. But this is a more question for discussion and for further projects than something I can answer now. Thank you very much.
Thank you, Alexey. Okay, first to raise his hand was Richard, then we have Fabio Briches, and then also Vairi Frolov, who asked me for a question. So please, Richard, you start.
Okay, when I raised my hand, I think you hadn't answered this, but I think you later on discussed it. My question was just if you have these entire functions, what does your Cauchy problem look like? And if I understood the discussion that you gave of that issue after I'd raised my hand, what you're saying is that there really are an infinite number of solutions. That is, that these operators really do involve the field infinitely far in the future and infinitely far in the past. Is that correct? And if not correct, why not?
No, in fact, you are correct, because including infinitely many derivatives, yes, we somehow excite infinitely many solutions, but they can be at least somehow classified. This is what I'm claiming. I'm not claiming that I'm kind of defeat infinite derivative problem or Cauchy problem, no. But I'm saying that I have, we got some idea of classification, and at least we have good, how to say, we think good about space-times for which the Lambertian forms, for which eigenmodes of the Lambertian form complete set of functions, which is purely mathematical consequence of this consideration.
Okay. Fabio, please unmute yourself.
Nice talk, Alexey. Can you hear me?
Yes, I can. Yes, I can.
Yeah. So I have a question. Probably, I'm not sure I understood everything correctly, but so you state that the appearance of ghosts is related to the background, right? It depends on the choice of the background. Is that correct?
Yes, I'm saying
and the
that
condition you put on the form factor that is valid for Minkowskian background does not ensure the appearance of ghosts in other background. Is that right?
Yes, absolutely.
Yeah,
because,
yeah. Okay. No, my question so is the following, because in that respect is not surprising, and it's related on the stability of your background. So it's not surprising at all that some background is unstable and can have runaway modes and so and Gauss modes and so on. So that's not, in my opinion, not much related to non-locality, but it's a general feature. And also, the condition you put on the spectrum of this operator resemble me too much a stability condition for the background. So probably the appearance of ghosts is truly related to the background, but it's not. My idea is that it's not much related to non-locality, but is a generic property of any dynamical system.
Oh, I would not say it like this. Consider this scalar model. You see, in order to gain ghosts, you really need to modify kinetic term. Infinite or finite number of derivatives is another question, but point is that just rolling in some potential, you will just shift mass, and the maximum what you can gain is tachyon instability, which is easily cured in any theory by saying magical words like "I'm going to the proper vacuum soon." You see here, things are depending on the kinetic operator, and this is not what you observe in a canonical two-derivative theory from a textbook. So it's not about non-locality explicitly, it's about high derivatives, it's about modifying kinetic operator here. But not like you could make, I mean, in JAR, you can make clear condition how to make theory well-defined in any background, you know. It may be unstable due to tachyons, but not due to ghosts. It's totally.
Oh, why any background? You in general relativity may have unstable background. That's not surprising. And also the problem you write right below on algebraic roots of this operator. You can easily obtain the algebraic roots of this operator from the algebraic roots of the box. So, well, that's I should probably.
Maybe I think we can discuss this better during the discussion.
Yeah, because it's going a bit detailed. We can definitely discuss it.
So just the last question by Valerie Follow, who asked me in the chat a while ago. So Valerie, maybe you can unmute yourself, and then the rest for the discussion. Okay. Valerie?
Hi.
Okay, good.
Yeah. I suppose my question is connected with the first one. It's about this box R equation. So the question, if R is a curvature and arbitrary background, it's nonlinear equation. So I don't know how we can speak about superposition. If R is a curvature for completely symmetric space-time, box of R is just vanishing. So what you have in mind when you're speaking about superposition of this eigenvalue problem? It's not really eigenvalue problem.
What I mean a very simple thing, actually. So yes, you're right. If you solve with respect to the metric, yes, it's a third order nonlinear equation, no question. But you see the jump happened a little bit when I said, look, this theory is great. And here I said, okay, this theory which you formulated, I said, okay, maybe we can consider it as quantum as long as we speak, where is it? Yeah, here, because here I say, okay, we can start to build quantum theory as long as we understood that Minkowski is great. So from this moment on, I kind of forget my idea of maximally symmetric spacetime, and I'm asking myself different questions. What are other solutions to equations of motion? And I consider this equation. And look, it looks like box R equal R1R. Forget about R2. Like box R equal R1R. It's an eigenvalue problem for the Lambertian. In a sense, if for the moment you forget about...
Sorry, box depends on metric itself. So for this reason, it's not linear eigenvalue problem. It's very non-linear one.
It is non-linear equation if you think about metric, but forget about it for a moment and think that you just solve eigenvalue problem for box. It was a kind, you see, it was a whole few pages in the paper, but a sense of this is like that. First of all, it was two-step procedure. Step number one, forget about metric dependence and just try to tackle the eigenvalue problem. Second step, once you obtain solution to your eigenvalue problem, try to see whether what you obtained is compatible with the fact that what you obtained forms indeed scalar curvature on your manifold. So yes, first of all, you obtain some solution for your R as a function of coordinates, and then you think whether metric which should build this indeed build this as a curvature. If not, you just say everything is incompatible. So it's kind of two-step procedure.
The second step includes some nonlinearity, so you lose the property that it's linear superposition, they gain the solution.
But second step is just a matter of check. But the first step is just solution of eigenvalue problem for box. So
okay, I think we can discuss this further in the discussion session because it's also this one a bit technical, right? So yeah, let's thank Alexey Koshelev again.
Okay.